Okay, welcome to the 2021 paper. This is an hour and 45 minutes, but it should take less than that. It's about 100 marks, and it is AQA, GCSE, higher paper, single science. All right, let's begin with question number 1. First of all, what's the shape of Buckminster Fullerene? Well, Buckminster Fullerene is a sphere. Could also say ball and football as well, so we're going to leave it there. I'm not going to actually write in all the answers for these, just for the most, but I will say them all. Give one use of fullerene. The best ones, of course, are going to be for lubrication, drug delivery, and you could also have, one of my all-time favorites, is it can act as a catalyst. Other options, of course, can be from the syllabus, such as has a high tensile strength as a fullerene, which means it can be used for tennis rackets. Let's see. Also, not as good is electrical conductors, so it could be used in circuitry. The next question, of course, is coming down, and we're looking at, here's a diagram of propanone. Well, first of all, I'm going to look ahead at the question and use it to answer. Complete the line diagram, use a line to represent each single bond. Well, I know that every bond is made of a pair of shared valence electrons. So that's 1, 2, 3 for each of the hydrogens. 1, 2, 3 for each of the hydrogens. And then, of course, between each carbon, I have another shared pair. That's 1, 1. But over here, I have oxygen, and I've got 2 shared pairs. So that's going to be a double bond. Also, I've got 1, 2, 3 carbons. So I can say that's C3. There's 1, 2, 3, 4, 5, and 6 hydrogens. And there's 1 oxygen over here. So I can use this to fill in the rest of it, which is going to be my carbon. 1, 2, 3, hydrogen, 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 and hydrogen. And of course, the molecular formula is C3, H6, and O. Next, also just to remember, carbon, hydrogen, oxygen are all going to be nonmetals, so this is a nice, simple covalent structure. And when I say simple, I don't mean simple as in easy, I mean simple as it is simple, which means that you're going to have weak intermolecular forces that are holding together, which is why it also will have a low boiling point. Next question. A graphite question. Graphite questions are quite simple because normally they will involve electrons between the layers. They will talk about the layers and how carbon should be making 4 bonds, but it's only going to make 3. And that means that the overall charge of this will be positive. The positive and negatives will hold the layers together, but it's pretty weak. Because it's weak, it's easy for these layers to slide off, which makes, of course, graphite soft and slippery. But at the same time, these electrons are delocalized, which means they can move between the layers. And as they do so, they can carry charge. So they are a good conductor of electricity because electrons are delocalized. Because of the 4 possible bonds, they only make 3. And that allows the electron to move through the structure, and that allows it to carry, and here's the best part, it will carry charge. So that should hit most of the points on that one out of the 6. It says your answer should in terms structure and bonding. So again, you need to talk about 3 bonds. Sorry about this, I am backtracking a bit. You have 1 delocalized electron, and it's between the positive layer of graphite and the negative electrons, and the force is relatively weak. All right, let's jump ahead and move on to this question's about gallium. Give the meaning of isotopes. Well, an isotope is the same element, which means it has to have the same proton number between all different versions of the isotope. So proton number must be equal between the different versions. And they want to know in terms of subatomic particles. If the proton number is equal, then of course the electron number should also be equal. And of course protons are equal to electrons. But the thing that's going to be different is that the neutron number will not be the same. And if the neutron number is not the same, I'd like to remember that the atomic mass is going to be equal to the protons plus neutrons, and if the neutron number differs, then the atomic mass will also differ between isotopes. Moving on to the next one. They want to know how to calculate the relative atomic mass of gallium. Well, they've given you the mass number and the percentage abundance, which makes it relatively straightforward in that you take the mass, you're going to multiply it by the percentage abundance, but we have to turn that into a decimal, so we're going to do that this way, 69 times 0.6, and then we're going to add it to all the other ones. So the mass number for the second one, the second isotope, is 71, and the percentage abundance for that isotope is 40, so it's going to be times 0.4. Overall, we then just have to simplify, and I've got my calculator. It's going to be 41.4, and that's going to be 28.4. So overall, we're looking at a relative atomic mass for gallium of 69.8. And they want it to 1 decimal place, so we'll leave it as 1 decimal place. Jumping on ahead again. Gallium is in group 3. Well, that tells me almost everything I need to know. If you're in group 3 and you are a metal, you're going to lose 1, 2, 3 electrons. If you lose 3 electrons, you're going to have a charge of +3. Oh, sorry, I am jumping ahead. Let's just go to the first part. Number of electrons. Well, the atomic number tells me the number of protons. The number of protons, if it's not an ion, will be equal to the number of electrons, which will then also be 31. That is the atomic mass. And 69 is going to be equal to the number of protons plus the number of neutrons. If I know the number of protons is 31, then I can just solve for neutrons, which is going to be 69 minus 31 is going to be equal to 38. Now, sorry about jumping ahead earlier. I also knew that this was group 3, and they want to know the ion for it, which means it's a metal. Metals will form positive ions because they will always lose electrons, which means if you're in group 3 and you lose 1, 2, and 3 electrons, they become +3. Gallium was discovered 6 years after Mendeleev published his periodic table. Give 2 reasons why the discovery of gallium helped Mendeleev's periodic table become accepted. Well, one is Mendeleev left gaps based on properties, and so it basically filled the gaps. He left for gallium. And of course, it was based on properties. The other thing is it gave validation. It proved his theory was correct, so it validated his theory. But the best part is, afterwards as well, it also showed it was repeatable because it wasn't just gallium. There were others that came later, but validation by scientists. Next one. Oh, please be aware that I am not filling in all the answers because I'm trying to get through this in less than an hour and 45 minutes. Much less if I can. Next, we have the questions about the extraction of metals. Element R is extracted from its oxide. And there it is. By the reduction with hydrogen. And there it is. The sum of the relative formula mass for the reactants is 150. And now they want you to come up with what is R, or what is the mass of R? Well, if they're telling me that this is going to be equal to 150, I now have to calculate for hydrogen, which is going to be 3 times 1, because that's the AR of hydrogen, times 2, because there's 2 of them in the molecule, plus oxygen, which is going to be 16, and there's 3 of them, plus X, which we're going to, actually I'll just leave it as R. Then I can just simplify that again, and I can go for 3 times 2 times 1 is going to be R6, and that's going to be 48, plus R is going to be equal to 150. Simplify, and R is going to be equal to 96. Brilliant. Now, I just need to look on my periodic table for the next question, identify element R, and I'm looking for which one has an atomic mass of 96, which is going to be molybdenum. Carbon is used to extract tin from tin oxide. The equation is below. Calculate the percentage atom economy. Well, I know atom economy is equal to desired product divided by the reactants times 100. Well, I know that I only want to have tin, and tin has an atomic mass, or relative atomic mass of 119. I now need to figure out the reactants. And that's going to be, again, 119 for tin, plus the oxygen 16, and there is going to be 2 of them, plus the carbon, which is 12. And I'm going to multiply the whole thing by 100, and that's going to give me 0.73006, and I'm just going to make it to, and multiply by 100, my mistake, move the decimal place over 2, and it's going to be 73%. You could put 73.0% if you prefer. Now, our first really nasty question, which is an evaluate question. Tungsten W is a metal. Tungsten is extracted from tungsten oxide. All the solid products from the extraction method must be separated from tungsten, which means, of course, that this is a problem. This shows the results of possible methods for getting out tungsten. They want me to evaluate, which means I have to give positives, negatives, and on top of that, I need to give my opinion. So I have a table, and let's start. I want to first start off with relative cost. If it's low cost, it's good. So carbon's good, hydrogen's bad, and iron is good. Next, tungsten solid, that's good. Tungsten solid, that's good, and tungsten solid, that's good. Problem. This also makes tungsten carbide solid, so I'd have to remove the solids, and it will now have a low atom economy. Next, carbon dioxide is easy to remove, but also it's greenhouse gas. Let's give that another negative. Then we have water vapor, very easy to remove, so I'll give that a positive. Then we've got iron oxide solid, and well, that's also it's a solid, positive and maybe negative. Overall though, let's take a look. We've got cost, negative, positive, positive. I now need to make a decision. I'm going to go for the iron. And the reason why I'm going to go for it is because I'm going to say it has low cost, and it produces pure tungsten, and only tungsten in that form. On top of that, the iron oxide should not be too difficult to remove from it, although the water vapor would be easier. In this case, I would actually write out the positives and negatives for each of them, and I would then come up with my answer in the end about which one I would choose. This is a question about group 1 elements. Give 2 observations you can make when a small piece of potassium is added to water. Well, we all know that it makes a lilac flame. So, that is your first one. You could also say that the potassium will get smaller. You also know that it forms bubbles because basically you see the bubbles coming off. It will skirt around the top of the water because it has low density, so it will float. Basically, when it says observation, it is what you see, and that's it. You can't say it produces hydrogen gas, or you can't say it produces hydrogen gas, yes, but why? Because it gives off bubbles. You're always looking for what you can see. Please do not put in, unless they say there's indicator, that it changes the color of the water based on the pH, because without indicator, it doesn't do so. Complete the equation below for the reaction of potassium with water. Potassium is more reactive than hydrogen, so hydrogen will be displaced. And hydrogen is a diatomic molecule, so it comes in pairs. Then Also, potassium is not just going to become KO, it's going to become KOH, also known as potassium hydroxide, a very strong alkali. This, of course, is not balanced because I have 1 plus 2 hydrogens on this side, which is 3, and I only have 2 on this side. If I put a 2 in front, because whenever I balance, I can only put a number in the front, now I will now have 4. That's 2 from the potassium hydroxide and 2 from the hydrogen molecule. If I put a 2 here, I will now also have 4 hydrogens. So it's looking pretty good. I have 2 times 1 for the oxygen. I have the same over here. The only thing is I have 2 potassiums here, so I'm going to put another 2 right over here. I could put a 1 here if I want, but it is redundant. Next, explain why the reactivity of elements changes as you go down group 1. Well, this is a nice review from going all the way back to chapter 3. First of all, I need to remember that group 1 elements, well, they're metals. And metals want to give electrons away to make an ion. With that in mind, I want to make sure that that electron can be left. So the larger the atom, that means there's more distance. Between the nucleus, or the positive nucleus, and the negative electron, or valence electron. If there's more distance, there's less attractive force. If there's less attractive force, it's easier to lose. So the greater the distance means it's easier to lose that electron, which means it's more reactive. The other example is, or the other reason why is, there's also going to be a greater amount of shielding. Shielding, of course, means that if you have your positive nucleus and you have a shell of electrons and another shell of electrons and another shell of electrons, they're going to shield an outside electron, allowing it to be more easily lost. Now, explain why the reactivity of elements changes as you go down group 1. This is 2 aspects. Distance increasing decreases the attractive force between the positive nucleus and the negative valence electron. And 2, the shielding also reduces the attractive force between the positive nucleus and the negative electron. But the last part is you're also going to be increasing the nuclear charge, or the positive nuclear charge, which is going to increase, and this is not good for this particular case, it's going to increase the attractive force. Which is the opposite of the first 2. But imagine you have a tug of war and you've got 2 people saying it's easier to lose and 1 person saying it's harder to lose. Overall, it's going to be easier. Next. Sodium reacts with oxygen to produce an ionic compound of sodium oxide. Oxygen is a group 6 element. They want you to draw the dot and cross diagram to show what happens when sodium and oxygen react to produce sodium oxide. Well, I'm going to start off with sodium, and I know it's in group 1, so I'm just going to give it a 1 electron in its valence shell, and then I have an oxygen. Oxygen's in group 6, so I'm going to do 1, 2, 3, 4, 5, and 6 to show that it has 6 valence electrons, and then I'm going to have this electron go there, because sodium is metal, oxygen is a non-metal, and the electron will transfer over. The only problem, of course, is that oxygen needs 2. So I'm going to make another sodium over here. And that's also going to lose its valence electron. In doing so, we're going to have a sodium ion, and I'm going to draw it with the right notation of brackets and a charge of +1, and another sodium ion, which is a bracket and a charge of +1, and now I have my oxygen ion as well. which is oxygen, with my 6 initial electrons in the outer shell, and my 2 new ones to show my dot and cross diagram, and its gain 2 electrons is -2. To simplify this more, I can put 2 bracket Na plus 1 to show my positive metal sodium ions, and I can then have my oxygen. Again, I'll put my 6 in that I started off with, little x to show that they took those from the sodiums, and -2. This demonstrates the electrons moving across, that there's 2 of them, and the oxygen is taking them both, getting a charge of -2. Why is oxygen described as being reduced? Well, I'm just going to write down oil rig. Whenever anyone says the words oxidation or reduction to me, I always write down oil rig. So it says that oxygen is being reduced. Reduction is gain of electrons, so I can just say that the oxygen atom gained an E- to become an oxygen ion. But it didn't gain just 1, it gained 2 electrons to become an oxygen ion of -2. Next, explain why sodium oxide has a high melting point. Well, first thing I do when they're asking about melting point is I need to determine what type of bonding occurs. Sodium is a metal and oxygen is a non-metal, which means it's going to have ionic bonding. Once someone says ionic bonding to me, I now automatically write in it has a giant ionic lattice structure. This also means it's going to have very strong electrostatic force of attraction between the positive ions and the negative ions. So between the sodium and the oxygen. So very strong electrostatic, I'm going to just abbreviate it, electrostatic force of attraction between my positive ions and my negative ions. And it's going to be in a 3D lattice. So you have many bonds, and it takes a lot of energy to overcome these bonds. So, looking at giant ionic lattice, going on to talking about the electrostatic force of attraction between the positive and negative ions. That's in a 3D lattice. It takes lots of energy to overcome these. And that's why it has a very high melting point. Question 5. This question is about salts. Name the salt produced by the neutralization of hydrochloric acid with potassium hydroxide. Well, I'm just going to circle the last part of the salt, which is chloric. I'm going to circle the metal from the hydroxide. And I can know that I'm going to make potassium chloride. Now, name it, so I better write it down as well. When I make a salt, I'd like to make a compound, and so the end's going to end in "ide." Write an ionic equation for the neutralization of hydrochloric acid with potassium hydroxide. This is one of the few questions in the exam I wasn't too certain about, because it's only worth 1 mark. So when they say ionic equation, very often you mean full ionic equations, which is a bit difficult for this one. So if they meant the overall or the net one, we could basically do just the hydrogen ion from the acid, the hydroxide ion from the from the hydroxide, and that's going to make my H2O. So that's my nice little net ionic equation. But it doesn't say that. It says ionic equation, which means it could be doing the whole thing, which is H plus and a Cl minus and another potassium and a hydroxide ion, and that could be making my potassium ion and my chlorine ion, and on top of that could make my water. Luckily it didn't ask me to put state symbols on, otherwise I'd run out of space. I guess it could also be asking for the potassium and also then for the chlorine to make the potassium chloride if I were to refer to 5.1. I'm going to go for all of them. I know it's overkill. Next, soluble salt can be produced by reacting a dilute hydrochloric acid with an insoluble solid. Well, they want to have copper, copper carbonate, copper oxide are insoluble solids. Okay? Which of these insoluble solids can be used to make a copper salt by reacting it with, and here's the key, dilute hydrochloric acid? I know that copper is very unreactive. That's not going to happen. Which leaves me with the other two, copper carbonate and copper oxide. Copper oxide is also not as reactive, but I can do it if I heat it or use pretty concentrated, very concentrated acid. But it's saying here it's dilute. It's also not saying that I'm heating it. So I'm assuming that it's at room temperature. I'm assuming it's dilute or pretty weak, which means I'm also not going to have that one. So it should be copper carbonate. But when I go down, luckily they give me some options, so I don't have to be that picky. Copper and copper, no, definitely not. Copper and copper oxide, no, definitely not. Copper carbonate and copper oxide only sounds very promising. And no, definitely not. So it has to be that one. A student makes crystals of magnesium sulfate. This is the method they used. They added the sulfuric acid, they warmed the acid, they added a spatula of magnesium oxide to the beaker, they stirred the mixture, they repeated steps 3 and 4, and they filtered it. They evaporated the filtrate gently until crystals started to form, and they left the solution to finish crystallizing. Give a reason for step 2, 5, and 6. I'm just going to go over to 2. You're going to warm it because, and I'm going to go back up again, it is to do a couple things. One, you're going to use it to react more quickly. And I'm assuming I'm using sulfuric acid and magnesium. That makes a lot of sense, except I'm using magnesium oxide, which isn't that reactive, so I could say that magnesium oxide is not that reactive. So, one, I would like it to react more quickly because magnesium oxide is not that reactive. Next, step 5. Repeat 3 and 4 until the magnesium oxide remaining in the beaker. And the reason why is I want to use all the acid because I want acid to be, and I love to use the word limiting or limited. And that way my MgO will be in excess. So it's to use up all my acid. Acid is not safe. Magnesium oxide, well, unless you get it in your eyes, is. Step 6, filter. And that is, of course, to remove your excess MgO. And there we go. How should the filtrate be evaporated gently in number 7? Well, if that's your evaporating basin, and there's a beaker, and you have some H2O in here, add some heat, and this is going to be doing it over a water bath, and that way you don't heat it too quickly, and the crystals don't explode as you do it. So, I think you may be allowed to get away with moving a flame in and out to ensure that the mixture doesn't boil too quickly, but you would have to be very explicit. Next, iron chloride is produced by heating iron in chlorine gas. The equation is 2 irons and 3 chlorines meant 2 iron chlorides. like I said before, get used to always looking at your molar ratios at the start of any question. Calculate the chlorine needed to react 14 grams of iron. Now, they want to have the chlorine, and they give you the iron. Well, to do this, we need to first calculate the number of moles of iron. So I'm going to come over here. I say they gave me 14 grams, and if I take mass divided by AR, I'm going to get moles of Fe. So that's divided by 56, and that's going to give me a whopping 0.25. Next, I need to figure out exactly how much I'm going to need. So I'm going to figure out the ratio between iron and the chlorine. For every 2 of these, there will be 3 of these. So for every 2 moles of iron, there will be 3 moles of chlorine gas. So I just need to figure out the ratio, and that's going to be 0.25. And I'm going to multiply it by the ratio, which is 3 over 2. And that's going to give me 0.375. And that's going to be my moles of Cl2. Now, do they want chlorine in grams, or do they want it in moles, or do they want it in volume? Calculate the volume, which, of course, I know if I have 1 mole of any gas at room temperature, that's going to equal to 24 decimeters cubed. And it doesn't matter what the element is. So I just need to now take the point. I'm going to go here. Take that. 0.375 moles. I'm going to multiply it by 24, and that should give me 9 decimeters cubed. There are easier ways to do that, but I just went the very long way. Okay, next question, 6.1. We're working through. This table shows information about 4 substances, A, B, C, and D. First of all, which substance could be a metal? For it to be a metal, it'll have to be, have to conduct electricity at solid and at liquid, which means there's only one option. And that has to be C. Next, explain why alloys are harder than metals. Well, first of all, you have to say that there's different elements in an alloy, and the different elements will distort the layers, and the distortion of the layers will stop them from being able to slide or make it more difficult. And that, of course, will mean that they are going to be harder than pure metals. So, different elements, they distort the layers, and which stops the layers from being able to slide or makes it more difficult for them to slide. Okay, let's take a look at the next one. A student wants to compare the reactivity of a known unknown metal Q to that of zinc. Both metals are more reactive than silver. The student is provided with silver nitrate, metal Q, zinc powder, a thermometer, and, well, normal laboratory equipment. So with this in mind, we're going to start looking at how to do it. I'm going to pause here and come back in a bit.